Okay, so we're looking at some more trig equations now, and we're looking at cases that have more than one solution, or potentially more than one solution, and we're solving 2 cos squared theta equals 1 for the domain stated 0 to 2 pi radians. So there's no, well, there's a b value of 1 there, so basically we don't have to make any substitutions. We need to rearrange first. So cos theta all squared equals a half. Therefore, cos theta is the square root of 1/2, positive or negative, which is positive or negative 1 over root 2. And I've just spotted a little flaw with the title. That should have been cases of more than one equation, because we have 2 equations, and basically if you look down here, we've got cos theta can be positive 1 over root 2 or negative 1 over root 2 if you don't mind the irrational denominator. So let's put it into its 2 cases. When cos theta equals positive 1 over root 2, we're going to work on that, and over here we're going to work on the other case when cos theta equals negative 1 over root 2. So we know that we have some exact values here because, and we're in radians, remember. Okay, so we're going to talk in terms of pi. So cos is a positive here and cos is a negative there. So I've got 2 sketches of the unit circle. Okay, so this one corresponds with that, and that one corresponds with that one. So we've got positive values of cos in quadrant 1 and in quadrant 4. And if we take the inverse cos of 1 over root 2, we get pi over 4 as the acute angle. Therefore, the acute angle down here is pi over 4. We've got the same pi over 4 corresponds on with the second case, but it's negative, so we need to look at quadrant 2 and quadrant 3. So we'll have pi over 4 as the acute angle there, and pi over 4 as the acute angle there. So let's find theta in each case. So for the positive case, we've got pi on 4 is an obvious one, and then we've got 2 pi. We've got 2 pi take pi on 4. Which equals 8 take 1 is 7 pi over 4. For the negative case, we have theta equals, looking up here, we've got pi take pi on 4, which is 3 pi on 4. We also have pi plus pi on 4. Whoops, try it back up there. Which is 5 pi over 4. So those are our solutions. Writing them in the order of magnitude, from smallest to largest, ascending magnitude, we have pi on 4, we have 3 pi on 4, we have 5 pi on 4, and we have 7 pi on 4. Final example, we've got one that looks terrifyingly difficult perhaps, but it's not, provided you can solve a quadratic equation. So solve 2 sine squared b plus 7 sine b minus 4 equals 0. where we have the domain in radians between pi on 2 and 3 pi on 2. So now it's not because there's a coefficient here in front of the b, but because of the type of equation it is, we can solve it as a quadratic. It is instructive to actually make a substitution for a different reason to what we've seen in the previous videos. So let x equal sine b, and so we've got a clearly solvable quadratic there, because we've got 2x squared plus 7x minus 4, as you can see from the substitution there, and that equals 0. And factorize that quadratic, we get 2x minus 1, x plus 4. Using the null factor law, we can solve that quadratic. So x equals a half, or x equals negative 4. Easy enough. So that means reversing our substitution. Therefore, sine b equals a half, and we have sine b equals negative 4. Now clearly this can't happen here. You can't get sine of something equals negative 4. Okay, sine has a range of 1 and negative 1. Okay, you should know that. So that's the range, and you know that it can't exist as negative 4. So that's invalid. We reject that. We work on the other one then. So using our exact values, we're in radians. So basically sine is positive, so we're talking quadrant 1, quadrant 2, and sine of pi on 6 is the solution to that, pi on 6. So the acute angle is pi on 6 there, and also pi on 6 there. So b equals pi over 6, or b equals pi take pi over 6, which is 5 pi over 6. So our solutions are b equals pi on 6, so that's supposed to be a 6, 5 pi over 6.